Class, we're going to go over lecture 35 today. It's going to be on titrations and also on a little bit more about pKa's, which we mentioned in the pH lecture. All right. We'll start off, like always, with a little review quiz from the last lecture. Okay, so this is how much sodium hydroxide is required to neutralize a 0.12 molar nitric acid solution. This can be similar to the what we did in the last lecture. So first you want to write out the chemical equation, make sure it's balanced. You're then just going from volume of sodium hydroxide or volume of nitric acid. So this would be like our A, and then we're going over to volume of B. Okay. And yeah, should be pretty straightforward using that. And if you're looking at the stoichiometry map, so take the volume and then use molarity to get to moles of nitric acid. Molar ratio takes us to moles of sodium hydroxide. Then we can use the molarity to go from moles of sodium hydroxide to liters of solution. And that should be our answer. All right. Here is another quiz question you could try. Okay, so we have 5 mils of HBr at an unknown concentration. We find that it takes 27 mils of 0.12 sodium hydroxide to neutralize it. What was the HBr concentration? So we did one kind of like this in the last lecture. So if you look at the neutralization equation, we know a lot. We know the volume and the molarity of sodium hydroxide. So that would be our A. And then we're actually not really going to volume of HBr because we have volume. We're actually looking for the molarity of HBr, so that'd be like our molarity of B. But we're going to use kind of a similar path. So we'll start with the volume of the sodium hydroxide multiplied by the molarity to get moles of sodium hydroxide. Using the 1-to-1 ratio, we can get moles of HBr. And then what we need to do at the end is just divide by the volume that we have in order to get the molarity. You can see that liters cancel, moles cancel, and we're left with moles of HBr over liters, which is molarity, right? And that should be HBr, sorry. HBr, not HCl. Oh well, okay. So that's how you do that equation, all right? So this is the answer we got, right? And it's like, how do we actually do this in like in real life? Okay, because this is a pretty real life question that you would see, and this is called a titration. So what happens? I'll go through a visual here in a sec. But you're going to add sodium hydroxide with a known concentration, and you're going to be able to keep adding it until your solution of HBr is neutralized. Okay. Once it's neutralized, you record that volume, and then you also know the volume of HBr. Sorry, I realize this doesn't make a lot of sense without a visual. So let's just move on to the visual. Okay, so here's how it's set up in a lab, okay? So we have our base of sodium hydroxide, okay? We know the concentration, and we can measure the volume as it comes down, okay? The acid solution, like in the previous problem, right, this was our HBr. We didn't know what the concentration was, right? It's unknown concentration. But we can just measure the volume here in this flask. And so what you do is you drip sodium hydroxide into the flask, and you just record how much volume it takes to neutralize the HBr. And the way you know it's neutralized is using an indicator. So as you're dropping sodium hydroxide in, these like pink clouds appear and then they disappear. And once you add enough drops to where that pink just totally stays and doesn't go away, that's where you know you've totally neutralized the solution. So at that point, you have a known concentration, a known volume, and then a known volume of acid, and you solve for a known concentration. So this is called a titration problem, okay? And this is what we just did right here. This is a titration problem, solving for an unknown concentration, okay? So we've already done these kinds of problems. I'm just kind of giving it a more formal name basically and showing you how this is done in real life. Okay, so here is what you might record if you're doing this in a lab. These are the numbers you might record. So go ahead and try and solve this problem. Okay, so we have 10 mils of HCl at an unknown concentration, right? So again, to kind of visualize this, you have this beaker here full of HCl. We don't know what the molarity is, but we do know the volume is 10.0 milliliters, okay? So we put 0.125 molar sodium hydroxide in a burette. So we have this burette that's dripping into here. And this is a sodium hydroxide solution. Molarity equals 0.125 molar. And volume equals, let's see. Okay, so we put 0.125 molar sodium hydroxide in a burette. The initial volume reading, so you'll have this volume reading up here, that's 15.65 milliliters. You slowly add the sodium hydroxide until the solution turns a faint pink. Okay, that's when your solution is neutralized. The volume reading is now at 24.59 milliliters. Okay, the volume reading on burettes are upside down to help you see how much you've added. Anyway, the volume reading is now at 24.59 mils. What was the HCl concentration? Okay, so we need to solve for this volume. So that's just going to be doing a subtraction between these two numbers, and that would give you the volume. So our difference in volume is 8.94 milliliters. At this point, we want to pull up the chemical equation. So we have hydrochloric acid plus sodium hydroxide, right? It gives us our salt and water. So this is the neutralization reaction. Okay. And then we set up like we have all the other ones. So we know a lot about sodium hydroxide. So this is like our A. And then we're trying to get over to B, which is HCl. We don't know the concentration of HCl. Okay, so we're going to start like we've done before. We have the volume of sodium hydroxide times the molarity, gets us to moles of sodium hydroxide. Use the mole ratio to go to moles of hydrochloric acid. Divide by the initial volume of the hydrochloric acid, and we can come up with the concentration of hydrochloric acid. Okay, so that's just the full how to do a titration problem. Okay, you might see some of those as we move forward. Okay, the other idea I want to get to in this lecture is relating pH to pKa and predicting the state of a molecule, because this is really useful in Chem 285. Okay, so let's look at this example. Amino acids you might have heard of, right? These are the building blocks of proteins. Each amino acid contains a weak acid portion and a weak base portion. So here's what an amino acid looks like. Okay, all of the amino acids have this general backbone. They just differ at this carbon right here. You'll probably learn like 20 amino acids. There's like 20 common amino acids. They all just have something different coming off of this carbon. But this portion here and this portion here are common in all amino acids. The reason they're called an amino acid is this nitrogen with the two hydrogens on it. This is called an amine group. Okay, so that's an amine. And this group right here with a carbon double bonded to an oxygen and double bonded to an OH, this is called a carboxylic acid. Okay, you don't need to know the names of these right now. You will in Chem 285. But this is why it's called an amino acid, right? Amine acid. That's why it's called amino acid. All right. All right, moving on. So this is a weak acid right here. Okay, so this is the weak acid, and then this amine over here is the weak base. So because this is an acid, it could give up a proton, right? And because this is a weak base, it could accept a proton. So there's a few different forms this could take on. If this acid gives up its proton, it would look like this, right? And that's without this one picking up a proton. If the amine picked up a proton, it would look like this. if this carboxylic acid gave up a proton and the amine accepted a proton, then it would look like this, right? So there's like 3 different forms that this could be in. Our body has a pH of about 7.4. And so we want to be able to make predictions as to what state is this molecule in, depending on the pH. Because whether something is protonated or not has everything to do with how acidic the environment is that it's in, okay? All right. So moving on, let's talk about this and then we'll see how to predict these. So we've talked before about how pH is a measure of the acid strength of a solution, right? It tells us, pH really just tells us what's the concentration of hydronium ions in a certain solution. pKa is a measure of the strength of an acid, right? Of a weak acid. So if a pKa is large, then the acid is stronger. If the pKa is small, then the acid's weaker, okay? So comparing pH and pKa, you can predict whether the acid that you're talking about will be protonated or deprotonated. Okay. Deprotonated would be if the acid gave up its proton. Protonated would be if the acid is maintaining its proton. All right. So let's just look at the carboxylic acid, for example. So a deprotonated carboxylic acid looks like this, okay? So this is deprotonated. And a protonated carboxylic acid looks like this. Okay, this is protonated. So proton aided, right? That's where it comes from. Okay, so the pKa of a carboxylic acid, right? pKa tells you about the strength of the acid. The pKa of a carboxylic acid is about 5. So if pH equals pKa, and these are just some things you'll want to memorize. If pH equals pKa, then you have about 50% of the protonated acid and 50% of the deprotonated acid, okay? A is acid, H is if there's a proton on it or not. Okay, so if this carboxylic acid was placed in a solution that had a pH of 5, right, and so then the pH equals the pKa, then if you had 100 of these molecules, 50% of them would be deprotonated and 50% of them would be protonated. And that's what it's kind of telling us. So if the pH is less than the pKa, the acid will be mostly protonated. Okay, so that should make sense. So because if pH is lower, right, the lower the pKa, the lower the pH, the more acidic the solution is. So let's say you put this carboxylic acid in a solution that had a pH of about 2, right? The lower the pH means the more hydronium ions you have in the solution. And the more hydronium ions or the more protons you have floating around, the more likely you're going to have a protonated form of the acid, okay? So you're going to have more protonated than deprotonated if the pH is lower than pKa. And the way to just memorize that, I think the easiest is to say, you know, if the pH is low, you have more acid, right? So if pH is less than pKa, you're going to mostly have the protonated form of the acid, okay? If pH is greater than the pKa, then you're going to have the conjugate base form, which, again, the way to memorize it is just if pH is greater than 7, right? So the higher the pH, the more basic the solution. So if pH is greater than pKa, you're going to have more conjugate base in the solution, okay? All right. So the pKa kind of says, it sets where if the pH is equal to the pKa, you have 50-50, right? And if the pH goes down, then you have more of the protonated acid form. If the pH goes up, you have more of the conjugate base form, right? So the deprotonated form here is like the conjugate base, and this would be the acid form, okay? All right, cool. Yeah, so high pH is a basic solution. Yeah, I would just remember that part. Don't worry about this part as much. It's a little more complicated. Okay, so going back to our example, right? So the pKa, remember pKa's are for the acid form, okay? Because the A in pKa stands for acid. So if we looked at the protonated form of the amine, then the pKa of this proton, or sorry, the pKa of this group right here is going to be about 9.78. The pKa of this group here is about 2.34. All right, so what that tells us, if the pH is 7, right, let's try and figure this out. 7.4, okay? So let's just look at the acid side. If the pH is 7.4, that means that, again, we have pH, and over here is the pKa of that acid. So pH is greater than pKa, right? So the pH is more basic. So that means you're mostly going to have the conjugate base form of this group, okay? So that means you're mostly going to have the proton, the deprotonated form of this group. Okay, and then if we look at the amine group, the pH is 7.4 and the pKa is 9.78. So that means the pH is less than the pKa, right, or more acidic. So we're going to have the more of the acid form of this group, or the more protonated form, okay, which is this one right here. So at the pH of 7.4, so in our body, this is what an amino acid actually looks like. You have the acid form of the amine and the base form of the carboxylic acid on the right. Zwitterion is a term that means it's a molecule that has charges on it, but it's electrically neutral. So for example, this has a positive charge on the amine and a negative charge on the oxygen. So positive plus negative cancels out. This is electrically neutral, but there are charges on the molecule. Don't worry too much about the Zwitterion thing. What I really want you to know is that given a pH and a pKa, be able to predict whether the acid form or the conjugate base form is favored for a certain acid or group. All right, let's go through this example. So human blood, again, like we said, has a pH of 7.4. So it says, figure out which form of phosphate is most common at this pH, right? So you could have phosphoric acid, you could have dihydrogen phosphate, or hydrogen phosphate. Okay, and these are the Kas, right? This is not the pK, this is the Ka. So first thing you'd want to do is use the equation we talked about where pKa equals the negative log of Ka, okay? Right, P of anything basically is a negative log of that thing. So pKa equals negative log of Ka. And so we can put all these three in our calculator and get the pKa's for each one of these. All right. All right. So this is just telling us the difference in the pKa and the pH, right? So you can see that if the pH is 7.4, okay, so if pH is 7.4 in the blood, then this pKa is going to be less than the pH. This is also less than the pH, but you know it's pretty close to the pH, and this is greater than pH. Okay. I'd say since it's 0.2, I'd almost just say that it's about equal here. Okay. All right. So if you're looking at phosphoric acid, you can see that the pH is much greater than that pKa. So that tells us that mostly the deprotonated form, or the conjugate base form of phosphoric acid is present, okay? And the conjugate base of phosphoric acid is going to be dihydrogen phosphate, okay? If you look at this pH, it tells us, again, that the pH is about equal to the pKa of dihydrogen phosphate. And so that means you have, again, pK refers to an acid. So that means if we're looking at the pKa for dihydrogen phosphate, then we're considering this to be the acid and this to be the conjugate base. okay? So we're saying that there's about equal amounts between dihydrogen phosphate and hydrogen phosphate, okay? So both dihydrogen phosphate and hydrogen phosphate. Okay, and then if we looked at this third one, we're saying pH is way less than this pKa. So you're only going to have a tiny amount of the phosphate, which is the conjugate base below it. Anyway, all this to say that you mainly have dihydrogen phosphate and hydrogen phosphate because the pH is pretty close to this pKa. All right, it's a little easier to see. Let me draw a graph of this. Okay, let's see if I can do this on the spot. Okay, so let's say this is pH on this scale. I think I'm going to pH. Oops, sorry. Okay, so we have pH. All right, so here I'm going to draw like I guess this would be like percent, I don't know, abundance or whatever. Okay, so first I'm going to draw phosphoric acid. Okay, so phosphoric acid, H3O, P4, and come down here. So this is like 100% phosphoric acid, right? And then let's say this is 50% in the middle, right? And this is 0%. Okay, so we said that when the pH equals the pKa, then the acid and the conjugate base are about 50-50, okay? So at this point, we'll say this pH is about 2.12. Okay, and we're gonna have another one drawn up here. Okay, so here is our H. Sorry, I wish I could do different colors, but I don't think so. This is our phosphoric acid. Okay, so it starts at 100, and then as the pH goes up, we start losing it. When the pH is equal to 2.12, it's about 50-50 between the phosphoric acid and the dihydrogen phosphate. Okay, and then it drops down to 0 as we go up. And then the pKa of dihydrogen phosphate is about 7.21, right? So which tells me that the next one I want to draw in is the hydrogen phosphate. Okay. And at the pH of 7.1, we have equal amounts of dihydrogen phosphate and hydrogen phosphate. Okay, and then the last one would be, oh, it's a bad one, but well, just phosphate, okay? I guess I'll put the charges in here. Okay, and then because the pKa of hydrogen phosphate is about 12.66, okay? At this point, we have equal amounts of hydrogen phosphate and just phosphate, okay? All right. So once you have this graph set up, it's pretty easy to say at any pH what the relative amounts are. For example, if I took the pH right here, we would mainly have dihydrogen phosphate. Okay, the question's asking about pH of 7.4, which is about right here, right? So it's more like this. So there's slightly more hydrogen phosphate than there is dihydrogen phosphate, but they're about equal, okay? All right, so that's the graph that I think helps visualize it if you're having trouble visualizing this. All right, let's go ahead and pause the video and try this one out on your own. Okay. It says human blood has a pH equal to 7.4. Okay, shocker. We've already talked about that. Figure out which form of carbonate is most common at this pH. Okay. Let's go ahead and pause the video and try this. Okay, so hopefully your first step was to convert Ka to pKa using the negative log. Okay, and then at this point, if you wanted to, I kind of like the graph thing. You can also just kind of think through it. I don't know, more theoretically or whatever. But if we looked at the graph form, we're starting with carbonic acid. Okay, so this is H2CO3. And the pKa of carbonic acid is about 6.4. Okay, so that means at that pKa, you have a 50-50 mix of carbonic acid and bicarbonate or hydrogen carbonate. And the pKa of hydrogen carbonate is about 10.3. So that means at that point you have a 50-50 mix of hydrogen carbonate and carbonate. Okay, so now if we take the pH is 7.4, so I don't know, somewhere around here, right? You can see that the most prevalent form of carbonate is going to be this hydrogen carbonate, right? Because you're going to have about this much hydrogen carbonate. You're going to have a little bit of the carbonic acid, and you're basically going to have zero amount of carbonate. So it should be hydrogen carbonate. Okay, cool. Hopefully that helps you visualize it. I think that's probably the easier way to go. All right. Okay, that'll be it for that lecture. And we just have one more lecture after this, and then we'll be done covering all the material for this class. Pretty exciting. So, all right, I'll see you next time.